about momentum. And that basic idea that is inherently why when you start to look at the functional dependencies here, you'll notice, for instance, the power number does not have viscosity, okay, in it. It's like, well, how is that possible? Because, why?
Because after a certain point, it's
turbulent. Good. Okay, that's all we need. One word and we're good. Okay, because once it's turbulent, it's inertial, it's no longer viscous dependent. Okay. So you should not expect to see that here. Of course, it is here because that's an inherent idea is to come up with a dimensionless number of how hard you're pushing. And this is how hard it is to push. That's ultimately what we have. A really important aspect here, the functional dependence that is circled in red, is to realize how quickly power goes up. Notice that there's a density there, not viscosity. Why density?
Probably how heavy what you're pushing.
Exactly. Okay, because it's a fluid. Okay, it's about how hard it is to get it out of your way. And so the density of that makes sense, that would be the thing, not viscosity, because viscosity is no longer the key player. Okay? Notice that it goes up with n cubed, and just for the record, a cube is a lot. Okay? And so square is a lot, and cubed is a lot more. Okay? And diameter to the fifth power is a lot more. Okay? And so when you start to take a look at the concept of the amount of power that you're going to have for an actual impeller, okay, the proportionality constant, by the way, is the power number. Okay, is basically if you try to make it a bigger diameter, power draw is going to go up tremendously, huge. Okay, and that's inherently why some of the things that you'll see for very large mixed tanks are actually tall. They're tall because you'd rather actually mix something that has 3 impellers that are smaller in diameter, because there the power goes up algebraically. You put 3 impellers in there, the power actually goes up times 3. If you make the impeller 3 times bigger, okay, it goes up times 3 to the fifth, which I don't know what 3 to the fifth is, if you calculate. It's a lot. Also related to here, which if you get into tank design, which I'm not a mechanical engineer, I want to pretend to be, is it also the torque goes up this way too. So you can kind of imagine the amount of torque that goes on trying to turn something that goes up to the fifth power. Pretty soon you break things. Okay, and ultimately the scale at which you can actually mix a tank effectively, we're talking real large scale, 40,000 liters, that kind of thing, is actually torque limited. Can't actually, your shaft is actually so deformed that it's actually like deformed like a half a turn by the time you get to the bottom of the tank to the torque of the actual components. You can kind of imagine it's hard to keep a seal or a bearing functioning under that kind of thing, let alone a bearing that is in a seal that has to be sterile. And so those are the constraints that you have to start the tank. So that's the thinking about dependencies aspect of stirred tank design, if you will. And then that leads to thinking about gas. So the reason why we put it in is pretty obvious. Wake you up. Why do we put gas in the tank?
Well, to get oxygen.
Oxygen. Okay, so the oxygen, if it's an aerobic process or algae, would be CO2, photosynthesis, whatever. You need to get you have gas transport. The other platforms that we talked about eat a lot of other different things. What other gas was one that we talked about? Pardon me. Nitrogen. Okay. The problem. Remember, the problem with nitrogen is super hard. N2 is an inert gas. And biologically, it's super hard to fix nitrogen. Okay. So for the most part, that happens in the roots of beans, that happens in the Haber process at high temperature for that. But by and large, N2 gas is pretty much an inert and biological process. Some exceptions would be anaerobic cyanobacteria at night when the lights are off. Something like that. And they're not going to fix very much. Yeah, all the other guys talk about this. Syngas is one, which is made up of okay. So carbon monoxide and hydrogen, and so close. Okay. So methane can be burned as syngas. Okay. So it's on the other side. So where I'm going to emphasize, of course, oxygen, because oxygen is the important one in the world of current biotech. You know, CHE cells, E. coli, yeast, and so forth. You can extrapolate all this thought process to the other gases too. Okay, the Henry's law will be different. Okay, and the constant and so forth. But the basic concepts of mass transfer coefficients and all, they're all the same. Okay, in that. They are predominantly the same because remember that gases don't typically like to be soluble in liquid. That's why we have a Henry's law coefficient. They would prefer not to be in there. Okay, if you don't use if they really, really liked to be in there, it would be something else. Who's the famous dead guy? Henry's law is on one side of the thermal book, and the other side was. Just think of the dead guy. There you go. Okay, Raoult's law. Okay, that has to do with because it actually likes to be in there. Most gases don't because hydrogen bonding in water systems. Okay, you don't know Raoult's law. We remember the name. Remember the name. You don't know why or anything else because it's some dead guy. Okay. So we may, in fact, have an exam where I'll tell you match the dead guy. Okay. Remember that hydrogen bonding, you know, water is all about kind of like hydrogen bonding to itself. Okay, so it really likes itself. Okay. When gases want to get in there between, they don't particularly like it. This is why you're going to see the functional dependencies that are a little counterintuitive. That is when you increase the temperature, the solubility goes down. Because you're making the water shake. And when you make the water shake, okay, it shakes the gases out of solution. So anyway, we'll get to that in a minute. So I put in how much. This is the number that I kept kind of saying. It's just a convenient thing. Okay. VVM is that number that as soon as you mention it, it means something to you physically. If I say 0.5 VVM, I know that I'm putting in half a volume of gas per volume of reactor per minute. And it doesn't matter whether it's a reactor that's a 1 liter reactor or a 1 million liter reactor. It's 0.5 VVM means something to me in my head. That's why it's a nice relative number. Okay. And what are the units of VVM? Oh, okay. Next, you're laughing at it. Per minute, that's all. Yeah. Okay. So it normalizes out the whole volume thing, but at least it gives you a time thing. The other interesting aspect of this is the conversion. So when you think of a biological process and you're blowing bubbles in the bottom of the tank, okay, you have that limitation of moving across the gas-liquid interface. But what is the conversion? Very, very low. Okay, because if you're running air into the tank at what percent oxygen and air, Marina? 21. Okay, what does it come out? 20. Very low. Okay. Think about what that means. What it means is that if you are really worried about, for instance, extent of conversion, for how many of you are in kinetic reactor design? Okay. Okay. So. Okay, so you have to realize that there you are actually trying to get reasonably high conversion, right? If you have a reactant, a gas going into the reactor, and you're having it coming out the other end, okay, what would be a like hopeful conversion that you would have? Yes. Yeah, okay, good. I like you're going. That would be great, right? 100% conversion, except you just paid too much for your reactor. Maybe close to 100%. And here we're talking about 2% conversion. Okay. When you have a reactor in which the concentration is changing from the beginning to the end, then it depends on how well it's mixed, i.e. plug flow versus CSTR. Okay? And the answer is different on how they are mixed from beginning to end because the concentration is different on one here to the other end. Okay? If I have something, so a CSTR will have a different conversion than the plug flow by virtue of the mixing that's involved in that reactor. Okay? If I have something that's going in 21%, it's going out 20, it doesn't matter how much you mix them or not, because it's essentially the same concentration from beginning to end. And this is really an important thing to think about in scale up, because as you scale something up, the chances of your gas phase being mixed are less. Because when you have a multi-phase reactor now, you can't just think of mixing in terms of one phase like you do the CSTR and the plug flow. That's like a homogeneous thing, right? Okay. In the case of a multi-phase reactor, it's possible for your liquid to be well mixed and your gas to be going plug flow from one side to the other. Okay. And then that answer will be different if in and out were dramatically different. But if they're not, then you can get away with sort of like an average concentration being good enough. Okay. So with that background there's some like other terminology you should be aware of. One is called gas holdup. Okay, it's called holdup because literally, if you just think about this, here you have your 100 liters of water in there. When you start to blow gas in there, it actually the tank gets deeper. Okay, it doesn't get greater pressure at the bottom because there's really no contribution to head associated with the gas that's there because the density, the bulk density goes down. But in fact, it will go up. In fact, it goes up pretty substantially. Okay. And so if you just look at it in terms of what, just simple geometry here, the volume is basically the height change relative to the relative height change. And that number can go up as high as 20%. And this is kind of important too if you start to think about things like productivity. If half of your reactor is air, because if you take a liquid sample out, right, you're only going to be measuring what's in the liquid, and then you say, how full is my tank? Well, it depends on whether or not you're like, you can get really sloppy really quickly in the bio world, be like, it's only 20% off. Because, do you have 120 liters in there, or do you have 100 liters in there? Okay. If this was a CSTR, where there was a constant, like a weir overflow, the actual liquid volume would be 80% that's in there, that's actual functional working volume, because the rest is gas, and there's no cells in the gas. They're obviously not doing any work in the gas, in production inside that. And so, again, it's a nuance, but it's a somewhat important nuance depending on the circumstance that you have. Plus, of course, this is really what's responsible for gas transfer. It's the amount, you have to have an idea of how much interface is inside there for the gas-liquid mass transfer to occur. And so not too surprisingly, gas holdup is at least a beginning parameter for writing down an equation about how much interfacial area will be there to transport gas. Okay. There's some others. This is gas holdup is a parameter here. This is a slide that I literally is now almost 30 years old. It was originally done with color thingies on the overheads. And I was trying to explain to people why mass transfer is so hard to predict. Okay. Gas holdup is, you have to have gas holdup to have gas in there for transport. Gas holdup is actually what causes a differential density inside. It causes mixing and so forth inside the tank. Okay. And so that is essentially a driving force for actual liquid circulation. You look at liquid circulation and mixing, and you say they sound very similar. What I want you to leave this class today understanding is they are actually opposites. They go against each other. Okay? Better circulation often is poorer mixing, and better mixing is actually often poorer circulation. We'll get to that in a minute. But let's say that we could figure this stuff all out. Okay? This is essentially the interface. This has to do with that issue of extended conversion and so forth. And then you'll notice the arrows are only pointing to mass transfer. There's no arrow pointing back. In other words, the amount of mass transfer does not affect the amount of holdup or mixing and so forth. Why? Because the conversion's so bad. Right? If I was working at 90% conversion, okay, and I was reacting away 90% of my gas phase, then obviously that would affect gas holdup. Okay? But if you're not really reacting that much away, you can kind of pretty much say like, oh, it's at 0.5 ppm. It's not like it's 0.5 ppm going in and 0.3 ppm coming out, okay? Which would be the case if you had a very good gas-liquid reactor. Okay? Which it's not, I say it, but it's not, generally speaking, it's not worth it because it's air. Okay? And you blow it into the thing and you do that. Now there are most definitely reactors where this becomes an issue, not the least of which is the one I explained to you that was a chemolithotrophic organism that was being supplied hydrogen, oxygen, and nitrogen. And it was done in a stoichiometric manner, which was 100% gas conversion. There is such a thing as a dead-end fermentation where you would actually react away 100% of the gases. Very hard to accomplish like this. What you do there is you use a surface aerator. That way you're always recirculating the gas through. So it's like a recycle, constant recycle to the system, so you can actually react it away, as opposed to blow it in the bottom, let it come out the top like you saw over the pilot plane. It's not worth recompressing distinct E. E. coli gas after it comes out of the reactor. You just compress what's in the room, and so forth as a result. So the next 20 slides or so are hopefully then trying to get you to understand the bits and the pieces of the arrows in this little graph. Okay? So where do we start? We start with understanding just kind of a little bit about bubbles. If I had a solid ball, okay, and I was to take that solid ball and then like drop it, okay. There's a long time ago, again, the impressions you get from the early life of, oh, a television exists in the neighborhood, okay, was like those first few ads you saw were with you for the rest of your life. And the one was a Pearl commercial, okay, because they were selling that. And they take a pearl and they drop the pearl inside of it, and it goes down very slowly. And of course, since it's going down very slowly, it must mean that it's thick and rich and good for your hair. Okay. I look at that now and go like, oh, okay, could I calculate the rate at which that thing would go down through there? And the answer is sure. Okay. It turns out there's another famous dead guy missing here. Who's that? The person who tells you, if I tell you the size of the ball, the viscosity of the liquid it's in, density of the ball, how fast it will sediment. Ooh, I think that from that people's MA guy. He claims an awful lot of things. Okay. And so, not Newton, no. Stoke's law. Another one of those, as you go back to your notes with a highlighter, famous dead people. Okay, so Stoke's law is basically the relationship here is that it goes up as actually I think it's diameter squared if I remember. I think it's probably may even be animated. Let me just check to see. Yeah. Okay. There. No. Okay. Question mark. There's no person there. Okay. So if I had an isolated sphere, and the sphere, it doesn't matter, if it's less dense, of course, it will go up, and if it's more dense, it will go down. It's the same law for each one. It's not a different law either way. And so if I had a bubble, there was a single isolated bubble, okay, you could, or quite frankly, it doesn't have to be a bubble. It could be a liquid, an immiscible liquid. You could take hexane in water, take a little drop, so on and so forth. But you'll notice that this is sort of this is the theory, this is the reality. So part of the thing is like, so it doesn't follow Stoke's law when I have a whole lot of them. One of the reasons it doesn't is because of what's called hindered movement or swarm movement. The easiest way to think about this for me is if I was to take a handful of sand and stick it into a beaker. And then as the sand starts to move down to the bottom, what happens is that the more of it's down in the bottom, every sand that moves down has to displace water up. So the more that it gets down closer to the bottom, the more water is squishing out between itself, and so it slows down as a result of that. The same is true of a gas, if you think about it. You have all these gas bubbles trying to move up towards the surface, but as they move up, of course, they're going to have to displace the liquid that was above them down below. If there's a whole lot of them, then they functionally create a wind in the other direction, if you will, that will hinder their movement up as a result of that. So that's a swarm phenomenon there. It's like hindered settling. This one here is, let me see if I actually got this equation. There's certain inside, yes. Yeah. There's certain equations that I see them every year. I go, oh crap, okay. I should correct that next year. I think I finally got it right here. LaPlace, one of our favorite mathematicians, sort of, maybe anyone remember LaPlace? Yeah, LaPlace transforms. What is LaPlace transforms? It's that way of solving differential equations by turning them into algebra problems and then finding the inverse transform to get the answer. Okay. Yeah, no, sort of maybe. Okay, yeah, and anyway, think how much you paid for your mathematics education. Okay, yeah, we will encounter Laplace transforms very briefly in this class, okay, because it's the way you deal with process control. Process control is almost always taught in the context of a Laplace transform. And then I will show you how to not have to. Okay. This, I'm not even sure if it's the same Laplace, but I'm kind of guessing it was because there was very few really smart people. Actually, not that true. Reality is the rest of the world was like doing real things. And only a few people had the luxury of what we do now, and that is mathturbation. Okay, so with that mat tossed here, this is the pressure inside of a bubble. Now, of course, it's going to be equal to the pressure outside the bubble, but if you think about it, surface tension is actually a force that is holding it into a bubble. And so if there's a force kind of holding it into a bubble, then the pressure has to be higher inside than it was on the outside. And not too surprisingly, then, the higher the surface tension, the greater that pressure will be. Okay? The other thing is if you see the R on the bottom here, means that if it's small, I have a much higher pressure inside. And so very small bubbles have a very high pressure inside them. Larger bubbles have a lower pressure inside them. That gives rise to, when you have very small bubbles, they're nearly spherical, because if you have, it's kind of like your basketball. High pressure, I pump it up to a high pressure, it's very, very round. And if I let the air out of it, okay, it's not quite so round. Okay. Remember that there's a force as this thing is trying to move upwards, and that force, and if that force is enough to deform it, they become flattened. If they become flattened, then they slow down, because there's a greater projected area that they're kind of going up. And so the point you get these big ones here, like a bubble caps, and that when we're talking, remember, we're talking about a lot of gas here. You have that 1,000-liter tank, and you're putting in 1,000 liters a minute. Okay, that's hard to disperse into all little bubbles, because all the little bubbles would like to do what? Coalesce. Okay, there's a word, coalesce, right? It turns out little bubbles don't like to coalesce, okay? Because they're like small children, okay? Have you ever seen small children play? It's like they're bouncing off each other, and they fall down, all that kind of stuff, and they rarely ever get hurt. It's awesome. I want to be small again. Okay, and in fact, if you think about it, there's a pretty high pressure, and it's like an inelastic collision, right? Those things, like the billiard balls, they hit each other and they go on. Okay, high pressure inside, they're more rigid, they tend to have elastic collisions. And then what happens is the children grow up, okay? And they're no longer in elastic collisions. Okay. Never mind. It's a joke. Okay. So the larger bubbles have a lower pressure inside, okay? As a result of that, they deform on impact. If they deform on impact, then they will stick together. Okay. And so as a result of that, you kind of imagine it's an unstable situation. Little tiny bubbles don't want it, they bounce. When they start to coalesce, they become more prone to coalescence. You can kind of imagine that if your goal here is to keep them small, why are we trying to keep them small in the first place? Okay. More surface area, but that's only half, right? Because the surface area per unit volume. It's all about trying to get as much surface area as you possibly can in a liter box. Okay. So breaking them up makes, for that same gas holdup that's in there, the smaller bubbles have a lot more surface area. You can kind of imagine for a given mass transfer coefficient, remember it's KLA, A is interfacial area per unit volume. That's the one that you can manipulate. And so breaking them up with an impeller, so on and so forth, is all about basically making that A bigger. And so coalescence plays a huge role. And anything that affects coalescence plays a big role. Like surface active molecules, which you find in biological systems all over the place. And so even in the medias that we tend to throw in there, things like yeast extract. What does that sound like? You take yeast and you extract it. Okay, you get all kinds of nifty little molecules in there, all of which have a tendency to modify the surface tension, and not too surprisingly, create other problems. So we'll do that with it. This is the 30-second slide on making bubbles. Okay. First of all, I will point out they're not bubbles, right? They're cavities. The reality is that a bubble is kind of like, the bubble, Mr. Bubble, all that stuff. Okay, and gas, liquid, gas, right? Okay, a cavity is liquid, gas. Okay, and so you're making holes in the liquids, so they are not really bubbles in a sense. There's a big difference between these two, and trust me, it's highly relevant to a biochemical engineer because when it goes from being a cavity to a bubble, it's called foam. Okay. And foam, generally speaking, is not a goal of a large-scale fermentation. In fact, it's a nemesis of it because you're trying to make all little tiny bubbles that won't coalesce, and then they all come to the surface and they bubble away. If I take a infamous Orifice Sparger, an Orifice Sparger is also called a pipe. Okay, it's just a tube. This is what's in the vast majority of the fermenters that you saw over in the pilot plant. There's just a pipe in the bottom there. The nice thing about a pipe is there's essentially no pressure drop. You can kind of imagine if you have like an aquarium sparger or something like that, you got to blow through little tiny holes and so forth. That's hard. And then you got to pay more money to compress your gas to throw it through that and so that. We'll talk about that in a minute. But at least from a standpoint of the design here, if I was to take that and start to, it's Friday. You can go to your favorite beverage place, get your soda, okay, and then you can start to gently blow bubbles in there and look like the total geeks that you really are inside, okay? Okay, so you can be sitting there with your friends, you can blow bubbles, okay? And do it very slowly, and then slowly increase the rate at which you blow, and you'll see that the bubbles don't get bigger in size, they come out at an increased frequency. This happens up to a certain point. There is a point at which the one, as it's trying to leave the orifice, is getting blown up bigger before it has a chance to escape. So under these circumstances, you end up with something where the high flow rates, where you tend to have a relatively constant frequency with which they escape, but they get bigger and bigger in size. You can kind of imagine that this is good for creating bubbles for interface mass transfer, and this is generally bad. Because what you're doing is you are putting bigger bubbles, but remember, bigger bubbles are not better. There's a lot of alliteration in that sense. Okay, so with that in mind, then, now, keep in mind, this is generally speaking a terrible way to make bubbles anyway, and that's why we have impellers. Okay. An important aspect of understanding is a lot of really large-scale fermenters, even some of the stuff like they did for penicillin, which were like 1 million, they either run half to 1 million, I'm not sure it was gallons and liters, and that would be a big difference, but they were enormous. Enormous as in like Groton, Connecticut, in a submarine base. They bought the Navy submarine base to field inside that field nukes subs. You can't do mechanical agitation in those things. It's not possible due to the issues I mentioned about torque and so forth. So an incredibly large-scale fermentation has to be done without here's the flip side of the two areas of relevance in the biotech field. The Ringe-Sparger is what you would typically see in a large-scale E. coli type fermentation. And so you kind of have your gas coming into here, and you have a ring with a bunch of holes drilled in it. In contrast, in the world of ChE cells, what you have here is a sintered metal sparger. Okay. Now, sintering is a phenomenon that you could experience on a late night in State College. Where would you go? 2,000 degrees. Okay. It's actually, I think I bothered, to be honest. What's happening? You take little tiny clay particles, right? And you mold it into a pinch pot or whatever else that you do, and then you sinter it. So that's what happens at 2,000 degrees, is that those little particles, which are largely silica and so forth, they melt, but they don't turn into glass. They don't turn into an amorphous material, because if you've ever made a piece of pottery, you'll know that it doesn't hold water, okay, until you what? That's sintering. Sintering, they're still porous. Glazing. Okay, good. So you've been to 2,000 degrees. Okay. I'm just kidding. Okay. Actually, I think I exposed my daughter. So what sintering does is it literally takes little particles and it melts them so that they're all stuck to each other, but they're not like so stuck to each other that you can't get anything through it, because that would be making glass. It becomes totally melted and amorphous, and that doesn't happen there. So you can imagine that the way this is created is you take little tiny fine particles of stainless steel, and then you actually bring them to the point where they start to melt and stick together, okay? And then you end up with like an unglazed pot made out of stainless steel like this. Very smooth, they're really kind of cool, and they're really expensive, okay? And they're really good at making small bubbles, unless you blow through them too hard. Because if you blow through them too hard, then they're all just going to coalesce on there, and then they just leave as big bubbles, which you paid a whole lot for the pressure drop there, only to make big bubbles, which you could have made by just blowing bubbles through a straw. Okay, so again, this is like an operational thought process then of like, oh, more gas into my reactor will make a higher mass transfer rate. But trust me, the answer to that is no in so many ways that, that this is just one more of them. And that is you do a poorer job of making bubbles in the first place. That means that your interfacial area per unit volume drops off, and your mass transfer and your oxygen availability of the reactor now goes to crap as well. Okay, so more gas is not better. Less is more, sometimes. Okay. The design of a Ringe-Sparger is quite a bit different. And you can imagine that if you tried to build one of these, okay, the chances of it actually working very well would be pretty bad. Okay. It's kind of hard to drill little holes in that, although you could at the learning factory if you get good on the whole piece of equipment. What? Not a drill press. Drill presses are terrible. Milling, yeah. Bridgeport, yeah, very good. Okay, so that's a much better date than the learning factory, by the way. Okay, they have this millions of dollars worth of equipment that you guys can go sign up and play with. Who here has learning factory certification? Okay, you guys don't even know what it is? Okay, there's literally some guy gave $1 gazillion, and there's on the edge of campus on the other side where students can go there and you can be certified to do everything from welding to Bridgeport milling machines to and so forth. It's a little secret because the mechanical engineers don't like MEs. Okay, but okay, it's there, and you can build anything you want. They actually have garnet-based high-pressure jets that will cut through 6 inches of steel, so you can actually make rims for your car if you want to. Really cool stuff. Okay. And of course, lathes and all that other guys. How do you know Bridgeport CNC?
Watch a guy on YouTube.
Okay. Okay. There's another alternative. Is that you could sign up and they'll actually let you during the training session. They will actually you get on one and you can say that I have actually done this before. I'm actually certified for everything, including on welding. Gary, huh? Okay. So, so at any rate. That was an aside. Okay, but a learning experience nonetheless. Okay, so the very precision, to 1,000th of an inch, you can do with a Bridgeport CNC. Drill little holes. What happens when you start to blow air in here? It'll all come out the first holes. Okay, because you need, if you think about it, the pressure drop from here to here has to be relatively small relative to the pressure drop coming out of the hole. If it's not, it's all going to go out the first hole it finds. Okay? And so it has to be designed in such a way for a certain range of flow rates. Okay? Here you can go from almost nothing up until the point where you're just starting to make big bubbles. Here you go from just dribbling it in through the first holes through an operating range where it'll actually come out. You kind of imagine that what sits above this is the impeller. Okay? So a Ringe Sparger is designed to basically try to distribute the gas in a very large tank. So it's not just running into a pipe here and there. So, at any rate, there you go. So now you know more than you ever wanted to know about Sparger design. They used to have the only company that I knew left in the United States that made these was Metallurgical. The only sintering 2,000 degrees left in the country for making these sintered metal pieces. And you can kind of imagine that what you needed to do for them is they could start with different sizes of material. It's like 10 inch butter. Okay. And then you sinter it, and then it has a range of operating pressure that depends on the flow rate and the sintering size that you're trying to use. Okay, so it'll be good for a certain range over which the flow rate from there up to a certain level, and then you do it by a surface area. You can get super large-scale versions of these things, but they're not fancy stainless steel, so on and so forth. In fact, most of them are ceramic, like what they find in the wastewater treatment community. They'll actually make spargers that, like that water treatment place that I was down in Philly. You can sign up, and you can call them up. They'll be like, "You want a tour of our food plant?" It's really, really interesting. Okay, great date. Okay, let's go to the food plant. And it's just literally fields full of these things with ceramic sparging heads in them there. That's how they do the aeration in the wastewater treatment plant. Making bubbles. What's after making bubbles? Okay, the very big picture of this. Okay, so we'll go back up one just to remind people that you're engineers. Okay, we all. You probably looked at it here. Who didn't look? You weren't looking. Okay, so 1 atmosphere is equal to how much water? Hydrostatic head.
Yes, I'd say
20 meters, 20 times 3. So that's actually not a bad guess. Okay, that's for those of you that have ever gone and jumped off the high dive or whatever here and that. At what level does it start to really hurt? No. Underwater. I mean, once you're underwater due to the pressure, hydrostatic head. Okay. But it was up there. We'll go to 33 feet of water. It's a number that you guys should, like there's certain things that are like, if you happen to work in an industry where you're working with hydrostatic head, this is equal to how many psi? 1 atmosphere is equal to how many psi? Oh, no. I mean, these are the 14.7, remember? And that was, yeah, it is, I think so. Yeah, it's not up there. So basically 14.7 psi per atmosphere. You guys memorize lots of useless things, right? Okay. And so this one's actually useful because you don't even know what a PSI is. Okay, you know what an atmosphere is because you're standing in it. Okay, 33 of water you can swim in or drown in actually. Okay, and so that gives you an idea now of the concept of scaling. Remember that oxygen transport, or any gas transport, is proportional to the partial pressure of the gas, right? Partial pressure of the gas depends on the absolute pressure of the gas. Therefore, at the bottom of a 30-foot tank, the pressure is 2 atmospheres. That's how much more than 1 atmosphere? Here. How much more? Okay, it's at the bottom of the 30-foot tank. How many, go ahead. I didn't think I knew it all. 1, okay, it's okay. So, it's actually 2, but I forget what question I asked. Okay, the point is that is it an important amount, right? We were already wavering on, like, what is significant, by the way, to you as a person? What percentage of something is significant? It depends on the circumstance, right? If it's how much I'm being paid, okay, I start to be like 10%, within 10% of like a faculty member we hired 5 years ago. Okay, that's actually not very significant for 30 years of effort, but okay, nonetheless, okay. The point is that it will depend, right? If I was working in DuPont at making some nylon monomers, and we were getting 1% conversion per pass. Okay, so significant improvement was like 0.2. Like, oh wow, 20% improvement in the terrible process. Okay, and so, but I would say 2 times is a lot. Okay, and so what I'm asking is that should you make a correction for the effects of mass transfer in a tank that's this big versus one that's 30 feet deep? The answer is the pressure goes up by factor 2. Even if so remember that the way the mass transfer thing works, right, is it's that mass transfer coefficient KLA times equilibrium C star, right, which is, help me out here. Yeah.
B minus C.
Now this is C here this is actually in the tank. Okay, and then there's that equilibrium one here, but what is it equal to? Yeah. 1. Okay. Well, we can always put a 1 in. It's always right. Cass.
4.
It's Friday. Please, I'm not making fun of you. I'm making fun of our discipline. Okay. Okay. So the equilibrium solubility of a gas in water.
So the concentration of the gas, Henry's constants, and the mole fraction.
There's that, and then where does that Henry's thing
At the
go?
bottom.
Except when you look it up, sometimes they report it as the 1 over, just to confuse you. So you look at half the books, it's the 1 and the inverse of the other. I don't know why. Don't ask me why. Okay, and then the other one was total pressure here. So this is the. Okay, so there is your. There's a mole fraction if you want to think of it here, multiplied times the pressure of the system. Okay, so you can see that clearly. Okay, if I make this twice as much, okay, that's going to improve mass transfer a lot. Okay, and so that is kind of hard to deal with. Meaning not in this class. Okay. In general, though, you can prove that if the gas phase was well mixed, which by the way it's not. Okay. But if it were, and we can get away with it because the extent of conversion is so low it doesn't matter. Okay. Then the pressure that you can use for this number would be the midpoint hydrostatic head in the tank. It's a nifty little proof. I can give it to you as a homework if you'd like. And you can prove that by integrating over the pressure from the top to the bottom of the tank, that will fall out to be the midpoint pressure for hydrostatic head inside the tank. Or we can just take it for granted. Okay, sounds logical, right? Okay, I like that one too. Okay. What about the gas? Remember, it's a gas. Water doesn't compress under 1 atmosphere. Gas does. Okay? So when I throw out that thing about VBM, I'm kind of like bullshitting, you know? Okay? Because it's like, you know, 1 volume of gas per volume of liquid per minute. Well, you got to specify what the pressure is, right? And I already told you from a logical standpoint, we probably do it with atmosphere, where there actually may never be any place inside the entire tank that is atmospheric pressure. Because you run it with a head pressure, usually about 10 psi. Why? Keep bad guys out. As long as you pay for an autoclave that can stand with pressure, I'm going to operate at a little bit of pressure, so if there's a leak, it leaks out, not in. Keeps the bad guys out. Okay. So the gas will change a lot in volume from the bottom of the tank to the top of the tank in a big tank. And you got to imagine if the gas is changing in volume, so is the interfacial area, because that's the size of the thing as well. So you think of a bubble that's small here, starting to expand as it goes up. As it expands as it goes up, its pressure goes down inside, because its pressure is actually greater than the hydrostatic head that was there, and now it's more prone to coalescence. So as it rises up through the tank, it's becoming more prone to it, and then all of a sudden, boom, crash, it can actually then start to coalesce when it gets to there because the size is now here. So you can kind of, I'm trying to throw out to you that, yeah, there's a lot going on inside the tank. Okay? And so it's really easy to convince yourself of, I have a great idea, I think it's going to be a lot better, that might not take into account all that's going on inside there. So don't be like disappointed in yourself. That's the point. Yeah.
Why aren't reactors big walls?
Because it costs you more money to blow air into the bottom of the tank. You have to compress the air that's there. Okay. We'll get to the aspect ratios of the tanks and so forth in a little bit here. And here I'm also then pointing out that issue of like the bubbles. Not only is it getting bigger, but when it gets to the surface, your whole goal is to make them small. But as you might think about it, if I was to take a straw and blow it into my, let's make it a stout, okay? Because it has potential for good head, okay? And I take that straw and I'm blowing it in there, and then I take my aquarium sparger out of my pocket from Walmart, which you can take with you to wherever you place. You can kind of imagine you start to blow through the aquarium sparger into there, what's going to happen? It's going to foam, right? Okay, it's going to foam a lot, okay? And so, whereas on one hand, your goal is to have small bubbles because that gives you interfacial area, tries to mass transfer, you then have it reach to the surface because it gets there pretty fast. Okay, and it becomes foam, and it's a problem. So what do you do when it foams? Time is up. This is our last slide. You add anti-foam, okay. And anti-foam, what do you think it does? It tends to break the foam, and it also tends to prevent them from making small bubbles as well. Okay, so the usual typical effect of an anti-foam is to also decrease your mass transfer coefficient. So you solve one problem by creating another. Plus, to be honest with you, a lot of the antifoams that they use are used not because they're the greatest antifoams in the world, because sticking antifoams will screw up downstream processing. They foul up membranes and everything else that you would be doing. And so you'd use something like a ethylene glycol, or not PEG, polyethylene glycol. Not a great antifoam, but it's neat because it stays in solution when it's cold. And so if you have downstream processing that is keeping your product cool so it doesn't break down a biologic, it stays in solution, doesn't mess with your membranes and so forth. And so it's not a bad antifoam because it does work a little bit and doesn't screw up downstream. Those are the trade-offs that you have in this type of process. We're done. Oh, on a positive note, what was the first lecture on? Yeah, R-chop, which was so he's been through 2 treatments. He got his PET scan today on his birthday, and essentially it's almost fixed.